Let's talk about antennas. Every single one of them has two completely different personalities. There's how it behaves when you're right up close, and then there's how it behaves from a distance. In this explainer, we're going to dive into these two secret zones, the near field and the far field, to really get a grip on the physics behind them and, more importantly, what it means for you out in the field.
All right, just a quick heads up, this is part 10 of a pretty deep 20-part series. It's all based on a detailed report about RF propagation from the RFI detectives. We're gearing this specifically for RF techs and engineers, so if you're someone who works with antennas every day, you are absolutely in the right place.
So what's the deal? Why the split personality? To really understand the difference between the near and the far, we have to go right back to the beginning, where the signal is actually born, right there at the antenna itself.
Okay, let's get into it. Every single radio signal starts its life as two separate, fundamental fields, and they're both generated directly by the antenna. So here's the key thing you got to remember. The voltage on the antenna creates what we call an electric field, or an E field, and at the exact same time, the current flowing through it creates a magnetic field, or an H field. So you've got two different causes creating two totally different fields.
Now, let's put on our detective hats and investigate that area immediately surrounding the antenna. This is the near field, and, well, things here are complex, they're chaotic, and to be honest, it's kind of a mess.
In this zone, the E and H fields are 90 degrees out of phase. They're completely out of sync. Think about it like two people trying to push a swing, but they're pushing it all the wrong times. Instead of sending that swing flying, they're just kind of sloshing energy back and forth. That's what's happening here. Energy is being stored more than it's being radiated away. That's why we call it a reactive field.
Let's look at a classic example. You've got a Hertzian dipole here, which is really just a simple, theoretical, straight-wire antenna. It's fundamentally a high-voltage source. So because of that, its near field is just overwhelmingly dominated by that electric field, the E field.
But if we flip that on its head, take a loop antenna, this thing is all about high current. So you can probably guess what happens. Its near field is dominated by the magnetic field, the H field, and in this case, the impedance is super low.
So how do we actually measure this relationship between the electric and magnetic fields? Well, we use a concept called wave impedance. It's really simple. It's just the ratio of the E field strength to the H field strength at any point you happen to measure.
The easiest way to wrap your head around this is to think about something every technician knows like the back of their hand. Ohm's law. It's basically the same idea. A high E field, which is kind of like voltage, over a low H field, which is kind of like current, gives you a really high impedance. And of course, the opposite is true too. But here's the thing. This chaotic mess right next to the antenna doesn't go on forever. As we move away, we get to the far field, and that's where a stable, predictable wave finally emerges. As you travel away from that antenna, the chaos just fades, and something pretty remarkable happens. That impedance, which was bouncing all over the place, super high for an E field source, super low for an H field source, it starts to stabilize and settle on this one single constant number. And that number is 377 ohms. Now, this isn't just some random number we pulled out of a hat. It's a fundamental property of the universe. It's called the characteristic impedance of free space. And what it means is that the E and H fields have finally locked into a perfect, stable, self-propagating ratio. So, out here in the far field, everything finally clicks into place. The E and H fields are in phase now, working together. They're perpendicular to each other, forming this beautiful, unified electromagnetic wave that just radiates energy away. The wave becomes a simple plane wave, which just means its behavior is finally simple and predictable. And this right here, this visual, is so important. It illustrates a critical point. An antenna's gain and its radiation pattern, those are strictly far-field properties. This classic donut shape that we all know for a dipole, it doesn't even exist up close in that chaotic near field. It only takes shape once the wave stabilizes way out here.
Okay, so you're probably asking, where's the line? Where exactly does the near field stop and the far field begin? It's a great question.
Well, it's not actually a hard line in the sand. It's more of a gradual transition area. Engineers call it the Fresnel region, or sometimes you'll hear it called the radiative near field.
But for practical purposes, engineers need a rule of thumb. So we define the start of the far field using something called the Fraunhofer distance. And you can see from the formula, it's not a fixed distance. It depends on both the physical size of the antenna and the wavelength of the signal you're working with. So, theory's great and all, but why does any of this actually matter when you're on a job trying to fix a problem? This, right here, is the crucial point.
This is where it all comes together.
This table pretty much sums up the whole story, doesn't it? The near field is reactive, its impedance is all over the map, and it's where you go to hunt down coupling and interference problems. The far field is all about radiation. It has that constant 377 ohm impedance, and it's where you have to be to measure an antenna's true performance. What this means in the real world is you simply cannot get an accurate antenna pattern measurement if you're too close, period. It also explains why that metal pipe or that bundle of cables running near your antenna can so easily couple with it, throw its impedance out of whack, and create a total nightmare of EMI. It's all happening in that reactive near field. So I'll leave you with this. The next time you're placing an antenna or you're chasing down some frustrating RFI problem, think about these two zones. Ask yourself, am I working in the chaotic near field or the predictable far field? Because understanding that boundary, that's the key to solving some of the toughest puzzles we face.